dia. Good morning. So today we're going to look at in particular, because it's good for the intuition, a simpler example with an ordinary differential equation. So I'm going to go slowly so that we can see the intuition, how multiple scales worked. We saw it as a tool, right? Plugging in and doing things. So for those interested, this is actually a very good book for methods in applied math. So I mentioned this last time, Bender and Orszag. The title is, let me sort of abbreviate, Advanced Mathematical Methods, for scientists and engineers. This is a 1978 book with many very good things, and I'm doing it and having the notes, chapter 11. Okay? So let me put the title. I think it's good to put the title because some of these might be new names for you. So not resonance, but the title of the first section is Resonance and Secular Behavior. Okay? So out of curiosity, I always like to ask you what you know, what you don't know, and I'm happy when you say you don't know, right? Because then it's material to be taught. So do you know what I mean by, of course you know what resonance means, I think, right? And do you know what secular terms mean? I would guess you don't know. Do you know what a secular term is? No? Okay, so we're going to see today. So it basically terms that artificially, or as I use the word the other way, in a spurious way, temporarily, you see what I mean by temporary, but in the power series mechanism that we've been using, generates a term that looks like a resonance. But we know there should not be resonance. That's why it's spurious. So how do we control that? Okay? And with ODEs, with an oscillator, you're going to see the intuition and I think even more the beauty of multiple scales or multi-scale analysis. Okay, so look at this. I'm going to do a summary of what's here, what's in the book. So if we look at the this equation, which is the harmonic oscillator, right? Just to remind you. So I'm going to remind some things from ODEs, right? We know that this guy here has a natural frequency, right? So let me call it, I don't know, this is the linear spring. So this is the forced linear spring, which is the mass spring system. Where we can buy this, and no friction, okay? So there's no damping. So we pull this guy oscillates, the harmonic oscillator, right? And the solution, if I want to divide by m here, and I'll divide it by m there, but I'm not going to do it. The solution has a natural frequency, the square root of k over m. So if I'm not forcing it, pull this guy, it will oscillate with that frequency. Now, there's a forcing term that could be periodic, so the equation that appears in Bender and Orszag is already, say, scaled. So the dot, let me write with the notation of the book. So this is the first problem that's analyzed in the book, okay, in chapter 11. Whoops. This is a little bit of a hiccup. Okay? So here, mass and spring constant have been normalized, right? No big deal. Now, what can happen if I force this guy with a cosine? Okay? So, what is in the other, let's see how much you remember. I'm going to do a little review. I'm going to do a little more than I was planning because I think it is good. So here we have that y of t should be, I think the book uses a capital Y for what sometimes we will write as this. So you see what I'm doing? This is the homogeneous solution, which depends on initial conditions. And this is the particular solution, right? So this particular solution basically is the non-homogeneous solution. So this is the homogeneous solution. This is the non-homogeneous, or as it is called, the particular solution to satisfy the non-homogeneous term. Okay? Now, when you see this, what comes to your mind? Look, if I don't have this cosine here, or if I don't have this f here, what is the homogeneous solution of this guy? That's very simple. We don't even need an ODE class, right? Course. Because this is basically saying, I mean, you can guess, right? A function, what is the function that differentiated twice plus itself gives 0 in the homogeneous case? Sines and cosines, right? Just like when we know also that exponentials are useful when, right? When you do integration term, whatever, integration factor. Okay, so the homogeneous term is a cosine and a sine. Now what happens if I put this term here? And how do I solve this? Right? So that's a little bit the thing I wanted to maybe refresh our minds, right? I think it's good, and it's good to have it on the video. That's why also I'm doing this. So if I have this equation here, right? So you can go, a very good book, undergraduate book is, say, Boyce and Di Prima. And if you want to solve this, right, you can use the method of undetermined coefficients, right? Do you remember these things? For the homogeneous part, these are constant coefficients. For the homogeneous part, we can go to the characteristic polynomial. Right? It's something that resembles us when we do the dispersion relation, because we put in a typical solution for this, and we get the characteristic polynomial, right? And then we solve for the roots. If it's two roots or double roots, there are the techniques to get the solution. And the method of coefficients to determine is that it will depend, this method for the inhomogeneous part, it will depend on how this guy looks like. Do you remember these things? So for example, if you have a sine or cosine here, okay, so if this is, say, a trigonometric term, so say, let me put it here, if g of t is a cosine omega t, then you put HP like this, you plug it in, and this becomes something you have to equate the coefficients. Let me open a little spot here. In our case, this A is equal to 0. Our case, A is equal to 0. Okay? And, and therefore, this implies that capital B, this guy here, is equal to 0. And we find, you guys can do the calculation, that capital A is going to be 1 over B minus omega squared. It's very simple, okay? If you don't remember this, it's very simple. You just, so what I'm saying is this. In the case A is equal to 0, there's no damping, okay? Therefore, if this is a cosine, and this is a cosine, this is a cosine, we're going to be able to cancel out the cosines, right? With the proper signs, right? And therefore, we're going to get an expression for A, which is this. Okay, so this A is this guy. Very simple. Now, there is this, right? Yeah. Now, the point is, this is okay. Okay, this is good if this omega here, let me see if I, this omega here is different from, my notation is bad, sorry. Usually we put here 0 for the natural frequency. Okay, so sorry, the notation. So this is the natural frequency for this guy oscillating by itself. That means I pull this guy, let it go, it oscillates. Okay, so sorry that I forgot the omega 0 here, omega naught. So if this guy is being forced differently from this guy, okay, and in the case of, which is your, of Bender and Orszag, we have this, we have that. Let me write again here. So back to the book, we have this. Which gives a solution So this is what I was about to say here. It's written over there. And what am I saying in words? What am I saying in words? So all this is very simple, right? Undergraduate ODs, but it's good to refresh our memory. So if I have this forced oscillator, which has natural frequency 1, because the mass and the spring constant are 1, the forcing, if it's not equal to 1, so that this doesn't blow up, this is the solution. Okay? So how do I calculate A and B? It's going to be initial position and initial speed, right? Because I can pull this guy and let it go, or I can also pull and throw it, right? So you see similar things we did with waves and stuff like that. So here is, if this omega here is near 1, or let me say it this way, is if omega is 1, we're in the resonant case, and this expression is no good. Okay? If omega is near 1, so nearly resonant but not resonant, we're going to have pretty big amplitude swings in the phase of the cosine. Okay? Okay. All right. So now, when omega equals 1, then it's going to be, well, the same constants, A cosine t plus B sine t plus a half t sine t. Okay, and if you look in the books of ODs, what has been done here? Do you remember that when this g here is a cosine different from the homogeneous solutions, you use this guy. But when it's on the forcing on the same frequency, right, you have to put a t here. That's the good guess, and you will see that things work. So for this case, if you check, is this t sine t. So this is the resonant term, right? Because you're forcing at the natural frequency, and the amplitude will grow linearly in time. That's the resonance, right? So the solution will be unbounded and will grow forever in time for the linear spring. Okay. So in what we're going to see next, okay, and what we're going to see next, including the multiple scale analysis, is how to deal with terms that appear like this that should not be there. You will see now why I say it should not be there. So these terms here are going to be called, in the power series expansion analysis I'm going to do next, are going to be called the secular terms. And we have to learn how to control the secular terms because they should not be there. Here, this is a genuine resonant term. In what we will see, the secular terms, I could have called them also like a spurious resonant term because they should not be there, right? But in asymptotic analysis, in the book, it's called a secular term, okay? So that's what we're about to see, okay? So this is a little bit of a refresh from ODEs, simple ODEs, right? If you don't remember everything, go back to an ODE book. Simple would be like Boyce and DePrima is a very good one. And now, let's see how this comes up in a power series expansion multi-scale. At first, not multi-scale analysis, because I'm going to do two asymptotic analysis of the same guy and try to convince you by the end of the day, well, not the end of the day, but at the end of the class, that multi-scales is really a shortcut, a very cool way of looking at things from a mathematical point of view. Beautiful mathematical trick. Okay? All right. So the first point in the book is this. So it's called the non-uniformity of a regular, you will see why, perturbation expansions. Okay, and the problem that we're going to look is another famous equation. With these initial conditions, let's put this initial condition. And this is a famous Duffin's equation. Okay, so have you seen Duffin's equation before? So Duffin's equation, it can appear in many different ways. So one way to think of it is because of this term, a nonlinear oscillator. It has many things of interest. You know, it can be, it's a dynamical system with chaotic regime. It can become bimodal and so on. Here, there's not as many parameters. You know, you can write a Hamiltonian system for it. But this is basically a model that you can think of it as a nonlinear spring. Okay, so you see this nonlinear term, as you stretch things, it sort of stiffens. So this can be also be kind of thought as a nonlinear spring. And here we're just going to look at it as a nonlinear oscillator, or from our mathematical differential point of view, a perturbation to our harmonic oscillator. Okay, so from the purely mathematical point of view, that's it, right? From our interest. But of course, we're interested in applications. That's why I mentioned about the applications. But from the purely mathematical point of view, a small perturbation. How do I solve this guy? How do I deal with this guy? So we're going to start solving it, okay? So our first ansatz, in the spirit of what we have done, so this is good to learn this because we can do all the details, we can see things, and then go back to the waves, the perturbation things we've done. You see, to connect and have a better mathematical understanding of it. So y of t is going to be a power series expansion in this form. Just like we did before, power series expansion in the epsilon. Last class we were doing power series in square root of epsilon because Rosales and Papanicolaou decided that that's not a big deal, right? So here's a power series expansion. I'm going to plug this in, and I'm going to get the first term, the zero term, next correction, blah, blah, blah. Let's see what happens, okay? Okay. So here, we're going to put the conditions. I should write this. Sometimes I forget that y0 is equal to 1. Okay, so what is being said here is that the leading order term will basically satisfy the conditions we have, and the high order terms will have satisfy homogeneous conditions, so it's already satisfied by the first term. Okay? All right, so now, you know, the book already skipped some parts. I'm going to not skip much more. Basically, we can write this. Look. Now I'm adding a little bit of my notation, but of course the book mentions this, is that I can write this. So look, right here we are seeing things in a very simple way, things that I mentioned to you in the previous examples, in the papers, whatever, that I said, look, we got to crank the wheel, do all the collecting terms and organize. Here's very simple. Here's the order epsilon equation. You know what I mean, right? Order 1 term. Here's the order epsilon term. So this is epsilon to first power. So let me just erase this. It doesn't confuse it. It looks like epsilon prime. Order epsilon equation. So this is the order 1 equation. Order epsilon equation. That this arises when I plug this in and I collect terms formally. This is the term that arises multiplying epsilon, right? And look, remember that I mentioned to you that in the power series expansion that we've seen before and was much more complicated, but in particular more complicated in the sense of just being more terms, right? Not more complicated intellectually that much, more complicated in the sense of the bookkeeping of terms, right? Organizing things. The housekeeping, as we say, right? The faxina in Portuguese and housekeeping in English. So here, look what happens. This is a linear equation. Remember I mentioned we get a hierarchy of linear equations that we have to solve to gradually go correcting our solution. This equation here is linear. Exactly, just went like this, because it's a guy who already solved for it, right? And if I keep on going, it's always going to be like this. Guys that we did before, okay? Okay, very good. So the solution to this one is okay, satisfies already this. At 0, it's 1. At 0, the derivative is 0. Okay? All right. But and the other thing too, remember I mentioned to you last time that, the first order equation at first doesn't feel the microstructure, this and that, da, 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 da. So here, see, the first equation is even homogeneous in this case. So it's a very sort of crude first approximation. Then you start getting more. more information. Okay. Now look what happens if we want to solve this equation. Now if we plug this in here, right, this is going to generate a term where we're going to do this. Look, cosine cubed of time is going to be 1/4 cosine 3t, sorry, plus 3/4 cosine t. Okay? So the only thing here is I'm not putting the minus sign. Who cares? So you can see that a complication is arising, or seems to be arising. Maybe you might not notice yet that it is a complication, but I'll give you more detail for that. So let me give you time. So what is something that makes me worry here? Look, this is a linear problem, and the right-hand side looks like this, okay? Or, right, this minus this, but the minus doesn't matter. So since this is a linear problem, right? I'm going to basically think that I have, my notation was G, so I basically have like G1 of t plus G2 of t. G1 of t plus G2 of t. Right? I don't care. I can solve one and the other. I mean, really ridiculous comment. Not even needed to be made. But this guy here makes me worried. Because this guy here will resonate with the homogeneous solution of 1. It's in the same frequency. The natural frequency here is 1. The natural frequency is 1. This one is already okay. It's another harmonic. Right? Remember, if we were thinking of waves, we had like k's, different k's in the Fourier series, whatever. This is like a different, would be like a different, it's a different frequency. It's not a different k, it's a different omega, because now we're in time. Okay? So this guy here is going to give me a headache, because it's going to make my solution grow when it shouldn't. Let me convince you it shouldn't in just a second. Okay? Let's see what else I can say here. So if I were, let me write here. So if we were to solve this problem, so if we were to solve problem order epsilon, we would get this. Look. Right? This is the resonant term, and this is called the secular term. Right? It shouldn't be here. It's strange that it is here. Let me write something. So our first attempt to write, whoops. Okay, so I'm abbreviating a little bit what's, so this is for epsilon small. So this solution for epsilon going to 0 plus is a good approximation. But we want a solution for a reasonable time interval. And look why the secular term is bad. So this is only good for times. So this is only good for times of order epsilon. But when time is of the order 1 over epsilon, look what happens. Let me give you a little bit of time to think about it. So this is why it's called non-uniformity. In the secular term. Because when time gets of the order 1 over epsilon, this times this becomes order 1. And then, you see, things will, beyond this, will start screwing up our ansatz that this should be respected. Right? Terms might, there might be a mixing of order, right? So this guy will become, this guy here will become order 1. This term here will become order 1 when it should be order epsilon correction. Okay? So that's not good. Plus, if you look at this guy by itself, you will see it will grow in an unbounded way. So one thing that it's important to look at is this. If we where's 114 here? Yeah. So multiply, let me put it like this, multiply Duffin's equation by dy dt and verify that we get an energy integral, or not integral, but energy conservation of this form. See if I got it right. Yeah. So basically, it's multiply Duffin's equation by dy dt. You can write it as a exact differential. You integrate. You get that this is equal to a constant. Right. So this tells us, for example, right? If epsilon is equal to 0, this is, and if you look in phase space, have you seen this for ODEs? Right? You know what phase space is? Right? Phase space, so we have, just for those who don't remember, phase space would be y dy dt, or the phase portrait, right? So would be this guy and this guy. So if you have this guy equal to 0, right, you can get circles or ellipses in phase space for the harmonic oscillator. And with this guy, you're also getting something close. You also get, so you get these curves here, okay? So I'm not going to write it. What does this say? This is an integral expression, right? So an integral conservation. This would be the energy conservation for this guy, okay? So the solution cannot blow up, right? So you see that this guy here, this is a way to say that the secular term is a spurious term. It should not be there because this guy grows indefinitely. But look, the solution doesn't grow indefinitely because the solution value plus its derivative is a constant. right? So that sort of confirms that, hey, this guy should not be playing the game. That's why I'm calling it spurious, right? As I mentioned before in the numerics, it should not be there. We had like a spurious damping, spurious diffusion. This is a spurious growth. Here, the resonance is okay, right? If you force something at the right frequency, it grows. Natural frequency. That's like when we're kids on swings, right? We use our legs to get sort of a frequency to make us go higher and higher. And there's also in the internet you see scary, sometimes videos. There's one of a bridge in California that with the wind. Have you ever seen this video? Oh, it's so scary. A bridge, this is sort of a suspended bridge in California. I don't know how to look it on YouTube. I haven't seen it in a long time, but put maybe on YouTube like bridge in resonance, resonant bridge, whatever. So you will see a bridge that due to the wind and poorly, I don't think it was that much, I don't know exactly if it was so much, it's a little bit of poor engineering design, but I think it was a very sort of wind on a very rare frequency. And the bridge starts snaking, and some of the car starts falling because it goes into resonance, and the amplitude starts going. Of course, it doesn't go forever. It cracks, and so it's very scary, right? One of the reason. I mean, you're going to guess, but the reason why soldiers cannot march over bridges. You can guess the reason, right? Because it's going to be everybody like this. There could be a stamping in a frequency that would generate some resonance. The bridge could break. So if soldiers come marching down the road, right, when they cross a bridge, they stop marching. So it's more of a random pounding, and then they go ahead. So here, this is legitimate resonance. Here, this is a spurious resonance. So it's called a secular term. Okay? All right. So let's see how to handle this. Okay? So we know it shouldn't be there by this energy conservation. So this is what the book calls, since I'm reading from the text, so let's see, let me read a little bit of part. I don't have to write everything. So it says, look, we have arrived, as the book says, we have arrived at an apparent paradox. We have shown that the exact solution is bounded, but the first order perturbative solution is secular. It actually grows in time. So what is the resolution of this paradox? So the book says, the resolution of this paradox is the summation of perturbative terms in a proper way, okay? So the book actually gives this example. Look, if you had a term like this, if you see an expression like this, this is the way the book sort of motivates. It's a good motivation. If you see something like this, right, which is a good approximation also as epsilon is small, but you see that as t is order 1 over epsilon 2, this term becomes order 1, right? This term becomes over order 1 and so on. But look, actually this is equal to e to the minus epsilon t. So if you sum all these guys, this is something that's, it's small, and as epsilon grows, there's no problem. But if you look at terms individually, right? So this is a motivation by the book, and I'm not going to go through the details. The book sort of doesn't go through all the details and indicates things. But if one does the summation, so the book says like this. Let me sort of summarize. If one takes care of summing up secular terms with some work, one arrives at page here, let me see. At a term, let me put it like this. Like this, for approximating the solution. Okay, so this is an interesting thing. We're gonna arrive at the same. So there's a lot of work that I'm skipping here. Okay, we're gonna arrive to a similar thing by doing a shortcut using multi-scale analysis. Okay, so from these secular terms, but adding up these guys, even in the book it's a little bit summarized. There's some, it indicates a little bit how one would do the exercise if you want to do it, but still he doesn't show all the steps. But one would then sum up and arrive to a term like this. I rather discuss and sort of, to some extent, sort of mention what is nice about this term. First, it's a well-behaved term, right? Second, it shows us a phase shift. Now that you know what I mean by phase, we've mentioned this many times, all the way from the beginning of the course. So let me not even put fingers, just look at you and say, the conclusion is that taking care of these secular terms that will appear over all this hierarchy of equations, right? Because there's no reason why a secular term should not appear in the next equations that very likely might have oscillators like this. And on the right-hand side, it's going to have more and more different forcing terms. So some sort of intermediate resonance-like term is very likely to appear here, right? Infinitely many times. So there's a secular terms. And those infinitely many terms that appear are, like in the analogy from the book, like these infinitely many time-growing terms here that appear that look like it's going to grow, but at the end, it's an exponential that decays in time. Okay? So, what is nice from the application point of view of reading what the summation gives us is that the nonlinear term, the small, perturbative, nonlinear term in Duffing's equation, that is in this nonlinear oscillator, what it really does is not make the solution grow and blow up, right? You might have chaotic solution, but in this regime, what it does is basically do a small shift in the frequency. Here it is. Look. Let me just write like this. See? The frequency for the linear oscillator is natural frequency is 1. So the solution would be cosine 1t. But now with the nonlinear term, there's this small frequency shift. Do you see what I'm saying? Right? So this is a very nice result that also from the application point of view, what is the nonlinear term doing? Okay, so now let's go to the multi-scale analysis and see what is the gain and what, now we have a little bit of the intuition of why that sort of recipe, right? As we saw multi-scale analysis in our previous 2 classes, whatever, it was a bit of a recipe that we kind of understood but worked. Now we're going to see a little better the intuition for it, right? Okay. So now multiple scale analysis. All right, so we're going to solve Duffing's equation. The same problem, but now with a slightly different technique, okay? it's also going to be a power series expansion. Same problem, power series expansion, but with a twist to it. And as I mentioned many times, I love this twist. I think it's very, very cool to see this, okay? Very nice. So, remember that we had a t. So in previous case, for t of the order, better to say, we had problems, right? The secular terms. So the shortcut is to use, let's put it 2 times t and tau, which is epsilon t. Okay, so one way of seeing this, maybe of course influenced with the text or whatever, is that when t is order 1 over epsilon, this guy is order 1. So this is the slow time. And let's see how it helps us in making this a shortcut in the sense of getting the same result with less work. Okay? And actually in a more, I would say, intuitive way. Okay? Now, so our ansatz is going to be y of t is equal to this. Okay, so you already saw this, how it worked to get the KDV, whatever. But now we're going to see it. We're seeing a slightly simpler, not so simple, simpler case. So what I'm saying is, I am now going to write a power series expansion in epsilon, just like before, to some extent. But now I'm allowing this wonderful mathematical trick, which is I'm going to pretend at first that I have 2 independent variables. We know, the book calls attention, hey, they are not independent. Our mathematical thinking that allows them to first be independent, they're not independent because t and epsilon t. But let's make them independent and see. So basically, right, I have a multifocal glass right now, but a long time ago there was a bifocal one that was divided, right? So this is a bifocal glass, mathematically speaking, looking at 2 different distances or 2 different times, right? And I want to see if these 2 scales, they interact and they give me interesting information. Here it will. Not only interesting information, it's going to give us a shortcut, right? Who doesn't like a shortcut? To get beautiful results, not results with less work, right? Optimizing intellectual energy, right? That's what we're doing. Okay, so plug this in. I'm not going to write this because it's simple. You've already seen that. Every time I take a time derivative of this guy, I have to use Chain's rule. I'm going to have time derivative here and here, and epsilons will pop out when I have time derivative here. Okay? So let's, I'm going to skip that. And so substituting, oops, sorry. Into Duffy's equation, we have the order 1 set of equations. Here's the order epsilon. Okay? So it looks more or less like we did before. And what is the first novelty that's appearing here? Well, first thing, the fact that I'm using partial derivatives doesn't really matter. This is still like an OD, right? Because it's only in t, not in tau. But I'm taking partial derivatives because I know this function is of two variables, as I am pretending mathematically to start with. Okay. Now here, I would say that this guy is the new guy that might help us. Right? Because look, if I cover this, that's exactly what I had over there. Right? It's exactly the first two equations I had for the more straightforward case. Straightforward intellectually speaking, but not straightforward in terms of terms, okay? So now I have this term here, and this term here, as we'll see, it will help us. Anyway, it's a new term, and it's already in the two variables, right? In the time and in the slow time derivative, okay? Okay, so now how do I solve this? Or how do I deal with this? Okay, the first one is just the same. Okay. So for the first equation, let me put it here. So the first one, I'm going to write it like this. Look, or we'll write the book, right? We're going to write it like this. Because I said it wrong. It's like the first one, but I have to pay attention. Let me write this because it's right. What I said, if I hadn't written this, I would be misleading you. Because this is cool, right? This is already, right? I said, oh, there's a novelty already here. No, there's a novelty already here also, right? A little bit, me going a little too fast. Pedagogically not very good. So here, look what this says. What this says now, and it's very important because this appears in waves, something that is in the notes, but I won't talk in this course because of the interest of time, which is modulated waves. In the case we have, right? Remember I mentioned to you that we can have, and we get a Schrodinger equation, which we get wave modulation like this, and actually you get a Schrodinger equation for the envelope. So this is actually the envelope, right? This is how the amplitude is changing, right? So this is in the notes, but I won't do it for the interest of time. Here we're going to have something analogous. Look what I'm saying here. Star, this almost doesn't look like a star, looks almost like an A. So star is complex conjugate, okay? So what we're saying here is this. Hey, y0, as I invoked it, it's a function of time and slow time, of two variables. So if it's solving this equation only in time, it's going to be sines and cosines. Now I'm just writing it using complex notation, right? This is sines and cosines, both of them. But the amplitude that for a harmonic oscillator was constant, now the amplitude can maybe change in slow time. So this is what I'm writing here. So this is interesting. This is saying, look, this guy, the first order correction is a sine in a cosine because in time it's like a harmonic oscillator, but in slow time, this harmonic oscillator in slow time, because this guy could be like this, see? I'm not drawing very well, but like this. Whoops, sorry, let me do a little bit better job. Like this. Right? This would be the slow time variation. Right? So it's the envelope. Right? Envoltória, as we say in Portuguese, envelope. So the envelope is slowly varying. Okay? So that's already a novelty for the first guy. I mentioned, oh, the novelty appears. No, there's already a novelty in the first guy. I went a little too fast. Okay? So let's keep this in mind. So is that okay? If you have any doubts, so this is an amplitude that could be slowly varying time. So something like this. Right? This is purely a cosine or a sine, but it has an amplitude that varies slowly in time. All right, cool. So now, okay, and for the time being, the complex conjugate is that for the time being, this amplitude also need not be real value. Okay, it could be complex value, but then you take the absolute value or whatever is needed. But for the time being, leave it as a complex value amplitude. Okay, which means if you multiplied all these guys together, you get the sines and cosines, you get the real part, you get something modulated in the real part, and you get the imaginary part, another independent guy. Okay. Now, if you plug this, see? This is a little bit in the spirit as we saw that, remember in the Rosales Papanicolaou paper you did a separation of variables, and then we plug it in to the right-hand sides. We get compatibility conditions that are, here we're going to have something similar in a simpler context. So now plug this guy into this equation. Okay, so the story is, let me repeat the story because I motivated slightly too fast, is that I solve this guy, which has already new ingredients, and I get this. Now I plug this into this guy that has this new ingredient, and I'm going to write the right-hand side. So right-hand side of order epsilon equation. Okay? And it looks like this. So basically this guy is equal to that, okay? The right-hand side. Is it okay? I mean, I hope I didn't do something very messy. So what I'm saying is that this guy is equal to this guy. Okay? By plugging this into here, I get this. Let me take a sip of water. What would you like to do next? Now, your instincts. We're getting close. We're getting close to the end of the course. And one thing we want you to get is your applied math, PDEs, differential equations, instincts growing. It's not going to finish here, right? Our PhD theses and research, we'll keep on learning, and keep on seeing more examples. But this is our first, maybe your first, playground to exercise these things you haven't seen before. So it's natural to hesitate, wait, but so if I get to this, what is the thing I would like to do now? What is my instincts tell me that I should do now? So we already saw something that gives us a headache. So what gave us a headache in the other strategy? I mean, the formal one that did not use two timing, right? Did not use a multi-scale in time. Was just one scale. We had secular terms. Secular terms were bad because they generated growth at intermediate stages, which there should not be growth, right? So now we don't want that to happen again. And it will be in a cleaner way because we don't have to do all that bookkeeping of trying to sum up terms that were left behind that would eventually generate this phase-shifted cosine. So to avoid secular terms now, There I couldn't avoid the secular terms. I had to keep them, and then try to sum them up. Now I can get them out of the picture. There I couldn't get them out of the picture. Now I can get them out of the picture. How can I get the secular terms out of the picture? I can basically ask for these terms here to be 0. Because if these bracket terms here, which are actually the same, if you check here, they're basically the same, right? They're just a minus sign. Maybe do I have a minus sign wrong here? Let me see. Minus, 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 plus. No, but it's conjugate. Yeah, the conjugate. Oops, I forgot here. This guy was missing, okay? So basically the same. So if I ask this guy here to be 0, which luckily is the same guy here, I kill this forcing term, I kill this forcing term, which are the secular terms, because these are the guys with the same frequency as the natural frequency. Are you with me? Right? So I have now what I can call a solvability condition. Remember that we had the solvability condition before. There was the compatibility condition that came from the Neumann problems, blah, 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 that the cell average have to equal. Blah. Here, the solvability condition, or we can also call it the compatibility, is basically different. Is this basically, I have to have this ODE for the amplitude to be 0. And I have another mistake. Please correct. Sorry, sorry, sorry. And you could have corrected me. I'm not complaining, right? I mean, just as an exercise. A is a function of only one variable. Slow variable. So where's my mistake? Here. And here. It's a typo. Doesn't matter. It's good, these mistakes. To some extent, it's good because it forces me to highlight that now I have this ODE to be solved in slow time. And if the amplitude of the modulation, which is a very slow amplitude change, satisfies this equation, that reminds a little bit like a linear Schrodinger equation. Look at the I here. If this guy here is satisfied, I kill the secular terms. At least for this stage of the problem. For the stage epsilon of the problem, I kill the secular term that I was not able to kill here. I had to deal with it. I had to sum it up. Okay? So let me go to the other board out there. Okay? Or maybe not. Let me erase this one so I'll stay. No, let's see. No, maybe it's good to keep this. Right, let me go here. So as the book says, let me use also the words of the book. To preclude secular terms, or secularity. No, did I write it right? Secu. As the terms, so good for you to hear different terms, right? That I was looking for. So to preclude, that is to remove secularity, that is secular terms, we have that. So this is like a compatibility or solvability condition. We have that. Whoops. Please come back here, the camera. I wrote this so fast. I forgot, okay? So please, you would see this in the notes, but please, I missed a 2 here. And I missed a 2 here. Okay, sorry. But you have this in the notes, but I wanted to point out for the camera, okay? Sorry. put it this way. We have to satisfy this amplitude equation. Which reminds a little bit the Schrodinger equation that appears in some places, right? This is like a Schrodinger equation. Okay? Then I'm going to sketch very quickly, okay? Then what happens is that use polar coordinates in the sense that you say that A of tau is a R of tau e to the I theta tau, right? So that you can have like, since this is a complex amplitude, right? So this is basically the height and a little bit the phase, but up, okay? You get this system of ODEs like this. Okay, then I'll skip the things, you solve, whatever, and, you know, and eventually this will lead, let me see what I can do here. Oh, here it is. This will lead that y 0 t tau Let me see if I copy this right, because I just copied something wrong. Okay, which then leads to this. Okay, so I'm skipping some of the things, the calculations are here. So basically you get this equation, you invoke a polar coordinate, it becomes this, the radius doesn't change so much, you solve it, it's going to be like this with the conditions, and then you find what these guys are. It's basically our good old friend, the cosine with the phase shift, right, and the next order corrections. Okay, so the story is that we got to this same guy here by killing one secular term, and in the previous case we got the same guy but with much more work by keeping infinitely many or a bunch of secular terms, a bunch of guys, and summing them up. So you had to go to a higher orders, whatever. So here this was like it, and this was due to the two timing, right? So which is here. Look, let me highlight here, see? The two timing, but this will become an epsilon t, blah, blah, blah. Anyway, so, and then doing the calculation, you get back, plugging in the values, the initial condition, you get this. So this is a nice way to see a little more in detail in a problem that's not so difficult. It's not that easy, right? But it's not so difficult as the waves one, where you might say, how did somebody figure out how to put, for the waves problem, we had a traveling variable, we had a slow time variable, we had a microscale variable, which was the xi, and so and so. So choosing your multiple scales and choosing your multiple scale variables is a little bit out of experience. I've seen many problems in many different scenarios where you have things operating on several scales, be it whatever field you're in, right? Something that you're sampling on a fast scale, like for, right, in the probabilistic modeling or an oscillator, whatever. But this is a very good example from actually a very nice book from 78 that gives this example to show how you can do different power series expansion and sometimes a minor modification, but very smart, tricky, of putting a second time made this shortcut, right? Much simpler to get actually the same result. And if you go to the notes, here you will see here the cosine t, the cosine with a phase shift, okay? And you will see that for early times, you can't quite see the difference. But for late, as time goes on, for larger times, like getting closer to 1 over epsilon, then you start seeing the phase shift. And you will see here that the peaks of the cosines of the different cosine approximations will start not mismatching, right? Which shows that actually this guy here is doing a good job and so and so. I think one of the solutions that's presented there is a exact solution that probably may be numerically done. I forget how they do it. But this guy, for a very long time, approximates very well. But this guy, the cosine Tino, starts having a little bit of a phase shift. The amplitude is okay, because look, right? There are some other cases where the amplitude also might vary, right? Here, actually, you solve the amplitude equations, and when you solve the amplitude equations, it tells you that, look, the amplitude is kind of okay for the first approximation. It's not changing, right? But the phase will change in a nonlinear way, but very slowly, because there's an epsilon here. Right? So very nice, right? So very cool. OD example, but that gives us the intuition of the waves in PDE's example. I still have almost like 15 minutes, I don't know, but I'm going to stop here because it's not worth continuing. Why? Because now we're getting close to the end of the course and so on, but next topic is basically a quick review of typical heat equation things, okay? I'm going to do heat equation, and then I will do also how do you solve the viscous Burger's equation, reducing it to a heat equation, which is called the Kohl-Hopf transformation, okay? And that leads us to talking a little bit, because if I give all detail, I mean, it's impossible to give all the details. As I mentioned, this is a course where the main thing of this course, particularly all of you good students, so on, the main thing of this course is first show a different perspective of PDEs, which I think is usually, as I say, more of a minority in PDEs here in South Latin America, which is more towards the side of functional analysis than asymptotics and other things. So it's to give you another way of seeing PDEs, right? That goes through asymptotics, modeling, blah, blah, and applications, right? So there's so many things one could do, including particularly for asymptotics. I just did some things of asymptotics of the differential equation. When I do the heat equation, when I do the Kohl-Hopf transformation to show you how to solve the viscous Burgers as a heat equation, because it's a nonlinear equation, but you can transform it into a linear equation, solve it, and then come back. That's the Kohl-Hopf transformation, very cool also. But then the solution looks, you solve it, but it looks ugly. You say, what the hell is going on here? And then to see a little bit of the solution, and that's one of the things also of this course, to see a little bit the solution, right? Not so only the technical aspects, which are important, say, from functional analysis, regularity, how many sort of estimates of derivatives you have. We want to see a little bit how the solution looks like. Then I'll give you a little brief introduction, very brief introduction of asymptotics of integrals. This was asymptotics of solutions. We already saw a little bit of asymptotics of equations, right? How to get KdV from this and that. So, as I was mentioning, this course is a course for you to see things that probably you wouldn't have seen, and it's not the typical PDEs course, at least here more in South Latin America. But the most important thing, that's why I give you some of these exercises, to learn how to learn, which is still my homework until today. As a researcher, in my bouncing droplet problems, I had to learn a little bit of quantum mechanics. We're always learning, right? I'm a professional student, right? I'm paid to study, and I hope many of you also will be for your life professional students, right? To be paid how to learn new things that people have not yet learned. So the idea of this course, and that's the idea of some of the homework, give you a text, is to learn how to learn. right, by yourself, so some guidance and so on. So I'll stop here. I'll come back to heat equation next class, next Wednesday, and we'll see the final classes, right? There's going to be heat equation one day, I think, and then probably next week. I don't know if I'll get next class, maybe just start a little bit of asymptotics of integrals, right? At least to pinpoint to you, and we'll see how we'll finish off the course.